Hello everyone, this is the second part from Basics of Organic Chemistry. In this video, we'll be dealing about the isomerism. Firstly, what is isomerism? Isomerism is the structures, the molecules which have the same molecular formula but different structures and different properties. So, if two two or more chemical substances have the same molecular formula but differ in properties and structure are said to be isomers. The isomerism can be grossly divided into structural isomerism and spatial isomerism. What is meant by this structural isomerism? In structural isomerism, the molecules have different structures due to the structures are different due to different connectivity. In spatial isomerism, what happens is the atoms in the molecule have same connectivity but the spatial arrangement is different. Now, what do you mean by spatial arrangement? The arrangement in three-dimensional space is different in these molecules. So the gross difference in the two isomerism, structural and spatial, is in the structural isomerism there is difference in connectivity of atoms in the same molecule. In spatial isomerism, if you speak about, the atoms are connected in the same manner in both the molecules or both the isomers, you say, but the spatial arrangement of the whole molecule in total is different. Now, in structural isomerism, there are various subtypes or types. So we'll be discussing them one by one. The first type in the structural isomerism being chain isomerism. In this chain isomerism, the isomers show different properties due to different carbon chain length. Chain isomerism is shown by compounds strictly having minimum of 4 carbon atoms. So writing it down, the isomers show different properties due to different carbon chain length. This chain isomerism is only possible if the minimum number of carbons in carbon chain is 4. So, giving an example, C4H10 butane, it is a butane alkane. So the two isomers of this can be N-butane and the second isomer is 2-methyl propane. If you see in this C4H10, only 2 isomers are possible. Only 2 isomers are possible. Now if we see another example, second example I'll write it for you, of pentane, C5H12. Now we'll try it out, how many isomers can this pentane have. First, every time we'll start with the straight chain formula. So this becomes N-pentane. The second one isomer, if we try, it becomes, by reducing the carbon chain length and adding a substituent. Now this becomes, according to repack nomenclature, 2-methyl butane. Now if we come for the third one, another this isomer is possible, that being 2,2-dimethyl propane. Propane because the longest carbon chain, this one or this one. Now this is a quaternary carbon, we'll talk it about later. Again, in the same chain isomerism, you can remember by heart these, or just remember these, as this can be asked as a sub question in any of the MCQ, like C6H14 has 5 isomers. This is just for quick enabling you to quickly remember the isomers if sub questions are asked in MCQ. C7H16 has 9 isomers. Next, C8H18 has 18 isomers. C9H20 has 35 isomers. And at last, C10H22 has 75 isomers. So I have given you a list of chain isomers starting from C4 chain length minimum, that is the minimum thing to have a chain isomer. So it has how many isomers? This butane has 2 isomers. Next to when you come to pentane, it has 3 isomers. When you come to hexane, it has 5 isomers. When you come to heptane or septate, you have 9 isomers. When you have come to octane, you have 18 isomers. When you come to nonane, it has 35 isomers, and decane 75 isomers. So it will be good for you if you remember or by heart the first 10 alkene chain isomer numbers. This is now the second subtype in the next thing in as the subtype of the structural isomer being the positional isomerism. In positional isomerism, the isomers show different properties due to different position of substituents, functional groups, multiple bonds on the same carbon. But the thing here being, the length of carbon chain should never change. The length of carbon chain should never change. So writing it down, the isomers show different properties due to different positions of substituents, functional groups, multiple bonds on same carbon chain. This is very important. On the same carbon chain, the substituents, functional groups and multiple bonds can translocate, but the carbon chain should not change. And in the context of this one being, the length of carbon chain should never change. Taking the example, the first example you'll be seeing is C4H8. Now this is butene. The positional isomer of this one will be but2ene, but1ene, or simply butene, this one being but2ene. Now this thing in an MCQ, it can be asked whether this one and this one are positional isomers, or whether this one and this one are positional isomers. The thing we should remember is this one. The length of carbon chain should never change, only the multiple bonds, the substituents and the functional groups can translocate on the carbon chain. So the answer is no. These both are not positional isomers, neither are they. So this is not a positional isomer of these two molecules. The next example for positional isomerism, second one, C3H8O. Now if you write this, H, if you fill H here, H3, H2, 3, 4, 5, 6, 7 and 8. So this is C3H8. This is propane, 1-ol or propanol, and the Positional isomer for this one will be propane 2-ol. And the third and final example, this is orthoxylene. This is metaxylene, and this being paraxylene. Ortho, meta, and para. The purpose of telling this example is, in the future, in the chapter alcohols, aldehydes and all, these positions are frequently used. So this should be, the positions should be remembered, and these are positional isomers. So in the next video, we'll be dealing about the functional group isomerism, metamerism and tautomerism. So please subscribe, like and share.